Thank you, everyone. So I'm from the Siemens Healthineers lab in Princeton. And since joining, I've been working a lot on MR reconstruction for compressed sensing. So I'm going to show a bit of what we have in the field now. So first, just a little bit of explanation about why we need compressed sensing for MRI. So in MRI, in general, what you image is the magnetic moments of nuclei, mostly protons, because that's what you have the most of in the body. And where it gets really interesting is that depending on the microscopic chemical environment, those protons are going to relax differently when they get excited. And so what we really want to look at is those relaxation time. That's going to give us soft tissue contrast. And then in order to get images, you need to modulate the main field of the scanner to do your Fourier encoding. So there's a lot of things you can do with that. You can image the basic relaxation time, so either the time that it gets for your field to recover in the direction of the main field, the time it takes for your signal to die out in the transverse direction where you're imaging, and more advanced protocol where you can image diffusion to get some idea of the orientation of cells or fibers in the body. You can measure blood flow, you can measure the velocity, you can measure blood oxygenation to do fMRI. You can separate water and fat, you can do spectroscopic imaging, you can do a lot of things, but fundamentally it takes time for multiple reasons. The first one is that all the interesting information is in relaxation time. So in order to measure that, you are going to have to wait for your tissues to relax a bit. So the excitation of the tissues is going to take time. Then how fast you can scan is also limited. So the K-space encoding is done by providing a spatial variation of the strength of the main field. And so to move from one frequency to the other, you need to change that modulation of your main field. And how fast you can do that modulation is limited by hardware constraint on the gradient codes that provide this modulation. So there's limited speed in how fast you can scan your K-space. And finally, there is a limited time window once you have excited your tissue before the signal just dies out or changes too much that you cannot just bin those K-space sample anymore. So that means that in MR, scanning is done as a succession of pulses, where you're going to do one excitation, acquire some K-space measurement, typically a line, and then redo the excitation and acquire another line. And so that makes it a very good modality and probably the best one so far to apply compressed sensing, because we really want to reduce this number of pulses that we need to send, because we want to reduce our scan time, and because all of that is implemented in software. So this is the one modality where you can actually do something that looks like compressed sensing without having to design a whole new sensor. So the way we solve compressed sensing, well, is just your typical penalized least square problem, where you have a data fitting term. So where you can really see that as a maximum a posteriori estimation problem, because the noise in MR is mainly Gaussian. And a sparsifying term. We usually use the so-called co-sparse model, where you put the sparsifying transform in the regularizer instead of putting it on the side of the measurement operator. So one problem with that is that the theory of compressed sensing works with really random sampling, which means that your measurement operator A is actually a random matrix. In MR, we cannot do that because we sample in Fourier. And so this is going to have some impact in the way we sample, and basically not much of the standard theory of compressed sensing really applies. So one quick way to look at it is if you were really sampling with a measurement matrix, then one measurement would be interchangeable with any other measurement. And so in particular, the energy of the measurement a priori would be IID. And we just don't have that in MR, because we know that we are measuring things that are images, and we know that the energy is concentrated in the low frequencies. So for example, very quickly, if we do a back of an envelope computation, let's say that you're going to do some random sampling in Fourier domain. So you do the random sampling with a Bernoulli mask with eventually what we call a variable density. So you're going to sample different frequencies with different probability, and you just look at the power spectrum that you get out. So the mean signal that you would get, so that's a mean on the mask. So it's not directly what you get from for one single mask, but it gives you a pretty good idea of what you would get in wavelet domain if you start binning frequencies together. So the probability, the density, is going to act as a filter on the mean that you get out, which means that if you sample with a variable density, actually your compressive measurement is going to have a filtering effect on the image that you get out. And the other thing is you can look also at the power spectrum of the noise that you get out of that, and that is also weighed by 1 minus the probability, and of course it's also signal dependent, which means that if you were just to do a uniform density sampling, you would get something that is, and you just do an inverse Fourier transform to reconstruct, you would get something that looks like your image plus a noise that is very heavy, low frequency noise. So something that doesn't look like white noise, but that looks like some kind of hazing. So instead, we do variable density sampling where we sample more densely in the low frequencies. That's kind of intuitive because if you have some a priori idea of where your signal is, you want to sample more where your signal is. And so this is the kind of images that we get just with a simple inverse Fourier transform, where there is a little bit of blurring, but that might not be visible because it's hidden under the noise. And there is a noise that is not quite white, so it would be exactly white for a particular distribution of the sampling density, but it's reasonably close to white. So now I'm going to show a couple of applications that are currently clinically available. So what I'm going to show now is FDA clear, it's for sale, and people can use it for clinical, routine clinical use if they want to. So the first one is for dynamic cardiac imaging. So in dynamic cardiac imaging, you want to do these 2D scans of the beating heart. So you want to do that either for a single slice, or you want to do multiple slices that are going to cover the whole ventricle. The application of that would be that once you have those multiple slices, you can measure the maximum volume of the ventricle, you can measure the minimum volume, and that gives you a good idea of the cardiac function. So without compressed sensing, there's just not enough time to acquire that in real time, which means that the standard non-compressed sensing protocol would be what we call a segmented acquisition. Segmented means that you're going to acquire over multiple heartbeats, then you're going to rebin the data together to, from multiple heartbeats, reconstruct consistent cardiac phases. So the problem with that is first, you're going to have arrhythmic patients, which means that one heartbeat is not going to look similar to the next heartbeat. Then when you try to rebin those data, you're going to introduce artifacts. Because what you're actually doing is mixing Fourier coefficients of different images and then trying to reconstruct that. Or you could do a real-time protocol, but then because the scan time is so short, you're going to have to compromise on resolution. So either spatial resolution or temporal resolution. So here, this is an example where, with an atrial fibrillation patient, where you can see, so if you do the segmented acquisition, you start to see those ghosting artifacts, which means that you start to see some multiple copies of the ventricle as the heart is beating. And otherwise, you can try to do real time, but you're going to get this very low image quality. So in that case, compressed sensing allows us to the real-time imaging. So this is acquired over a single heartbeat, and you can see that we get much better spatial temporal resolution, and we don't get these ghosting artifacts anymore. So that means that it's not just going to reduce your scan time, but you also get patients that you couldn't scan before that now you can scan. And so this is, if I can get it to move, yeah. So the single slice protocol, because it's real time, we could actually do it in free breathing mode. So, so we can acquire single slice in free breathing mode. If you want to be able to compute a consistent volume of the ventricle, you still need to do that in breath hold, because otherwise you're going to have multiple slides, but your ventricle has moved from one slice to the next, and you cannot really approximate the volume of the ventricle by the surfaces that you measured in each slice. So in that case, the non-compressed sensing protocol, again, assuming that you can scan the patient, that would be a multiple breath hold protocol, because it would take some 5 or 6 minutes to acquire all the data you need. So your patient needs to hold his breath. You scan while the patient is holding his breath. Then you need to let the patient recover. Then you're going to ask him to hold his breath again. And again, this is a patient, so this is actually a pretty exhausting protocol for him. So in that case, with compressed sensing, we can shorten that protocol to a single breath hold, to some 25, 30 seconds. So now one single breath hold and we're done. And so you see the two stacks of images, and there's pretty much no visual difference. And actually, in clinical validation, on pathologic patients that were not able to hold their breath properly, or with arrhythmias, or with some bulk motion for any reason, we saw some cases where we actually got better estimation of the cardiac function with compressed sensing than with the standard protocol. Okay, so I thought I would add a very little bit of math just to make things more interesting, but not too much because I would probably say something wrong eventually. So as you saw, we have this co-sparse regularization term, which means that at some point in our reconstruction, we need to solve the proximal operator of a wavelet transform. And typically, we use redundant transform because you avoid blocking artifacts, your images just look better. The problem is that proximal operators don't work very well in general with non-separable transforms. So that means that you would have to put another algorithm inside your proximal gradient or your ADMM in order to compute that proximal. And the other problem is that if your transform is redundant, when you compute the wavelet transform, you expand the size of the image. And we're looking at high-dimensional object, so this is 2D plus time. So if you just double the size in each dimension, that's multiplied by 8. So when we're looking at things like GPU implementation, when we developed that, it was in 2013, 14, 15. At that time, high-end GPUs still had only 4 gig memory. So actually, for high-performance implementation, it was also important to reduce the memory space. So, and at that time also, Berzelkas published some interesting papers on extending the ideas of incremental or stochastic optimization to non-smooth function. So basically, you want to do your stochastic gradient, but instead of doing gradients, you want to do stochastic proximal optimization. And it turns out that works. So similarly to stochastic gradient, you need to have some notion of a decaying step size if you want to converge. But basically, if you can write your proximal as a sum of atomic proximal operators, then you can have an algorithm where you're going to solve only one of the terms at the time. And so this is what we're doing in what we call sequential cycle spinning. So we have this redundant wavelet transform, and we're just going to split it as into a sum of decimated orthogonal wavelet transform with different initial offsets. And so what we do is we plug that into a proximal gradient reconstruction, where at every iteration, we just regularize one orthogonal wavelet transform, and we shift that offset in time. So that gives us pretty much as good result as using a primal dual to solve the full proximal at every iteration, but with much less time and much less memory footprint. So the second application that I'm going to present is something called compressed sensing grasp vibe. So vibe is just the name of the excitation sequence. So I'm not going to go into that. But grasp is more linked to the sampling pattern, and so this is more interesting, more related to core compressed sensing. So the application for that is for oncology. You want to do a contrast-enhanced dynamic scan. So the idea is that you inject a contrast agent, something that is going to make your image look brighter, where the contrast agent goes in the body. and you want to look at where this contrast agent goes over time, because let's say you have different types of tumor, different phenotypes of tumor are going to be vascularized differently, and so they are going to enhance differently under that contrast agent. So those are typically long scans because the temporal scale of the that you want to look at for the contrast agent is typically at least 2 minutes. So that means that your patient has to breathe at some point during that scan. And so with GRASP, what we managed to do actually is to turn this into a free breathing scan. So where we do a continuous acquisition in free breathing mode, and then we figure out how to reconstruct after. So the standard protocol to do this is that, well, a priori, you would know that there are some particular time points that you're interested in. So you would inject your contrast. Based on the injection time, you would guess at what time you want to image. And when you want to image, you're going to tell the patient, OK, now you hold your breath. And then you do your scan. Then you let the patient recover. And then you ask him to hold his breath again. And you need to do that typically for 4 times. And the catch here is that if something goes wrong, you cannot rescan. Because the contrast has been injected, you would have to wait at least a day for the contrast to completely wash out before you can try to scan that again. So that's a very difficult protocol to do. So with GRASP, what we're doing is just a continuous scan that is free breathing, and that we're going to reconstruct at high temporal resolution. So the way this is done, so what GRASP stands for is for a golden ratio angle. That's the GRA in GRASP. So golden ratio means that we do a radial sampling. So radial is inherently good for this kind of free breathing acquisition because you always go through the K-space center, you always acquire the low frequencies, and so your motion artifacts are going to look more like blurring than like really ghosting when you see those high frequencies that separate and multiple copies appearing. So in general, radial is good for motion compensation. This golden ratio radial has a specific property that the angle between 2 successive spokes is 1 over the golden ratio. And that essentially guarantees that no matter how you bin those data, you are always going to be reasonably close to uniformly covering the angular space in your K-space. So that means that you scan those data, and then a posteriori, you can decide how you reconstruct it. So for example, you can do 1 single static reconstruction for everything. So that is important because that is an image that you can show to the technologist at the scanner so that he can quickly check that the field of view is correct, the image was correctly acquired. So that means that once you have that, you can let your patient go, and you can figure out how to get the final clinical images later. Or you can do different types of rebinning. So for example, be closer to the standard non-compressed sensing protocol. Or you can even dynamically decide the temporal resolution that you want. So typically, in the pre-contrast phase, you're not supposed to have much temporal dynamics, so you can reconstruct at low resolution. The arterial phase is just right after you injected. So you're going to see some very big spikes of contrast agent here in the arteries and in the vessels. And so here, typically, you want to reconstruct at much finer temporal resolution. And then as the contrast starts to wash out in the vessels and to more diffuse in the rest of the body, again, you can afford to have lower temporal resolution here. And so when we reconstruct that, actually, the reconstruction needs to be able to handle that. And that is a difficult problem because now you're talking about very non-uniform sampling where you can have one image that has 10 measurements and the next image that has 20. So one of the problems that we had to solve for that, and again, that is something that you wouldn't really have in theoretical compressed sensing, is that you need to do some preconditioning in your reconstruction. That's because you do this non-Cartesian Fourier operators, which means that you oversample the low frequencies, and so that introduces correlations in your measurement operator. It's not orthogonal anymore. And so if you want to invert that, you need to do what people in medical imaging call density compensation, which is basically apply a filter to compensate for those correlations. So that is very well known in the tomography community, because this radial sampling actually is very similar to what would be done in a CT scan. Up to a Fourier transform, you have the Fourier slice theorem that tells you that the radon transform is equivalent to this radial sampling. So people in CT reconstruction have been doing that all the time, but they have been doing it for direct reconstruction. They have been doing it because when CT was developed, iterative reconstruction was too expensive, and so they wanted to figure out direct way to reconstruct. So that means that they haven't looked at it for undersampled scan. And also that, funnily, there is still this idea in the CT community that if you're going to do iterative, you don't need to do this density compensation. Whereas from an optimization point of view, you know that, yeah, of course, you can do a gradient descent if you want, but if you precondition it, you're going to converge much faster. And so for a radial scan, the sampling density just decreases linearly with the k-space radius. And so if you're fully sampled, the filter that you would have to apply to compensate is just a ramp filter. Now, our case is a bit different because we're dealing with undersampled data. And when you have undersampled data, it's true that the density decreases linearly, in the sense that if you integrate the energy of the measurement over a k-space radius, that is going to decrease in 1/r. But it decreases for different reasons. You have your k-space center where you're oversampled, and so where you are going to have singular values that are higher than 1. And then as you go away from the k-space center towards the periphery, well, where you have a sample, you're still going to get a singular vector with an eigenvalue 1, but now you're going to get a null space in that array. And so if you just try to apply a ramp filter here, actually, you would mostly be blowing up the undersampling artifact. You would not be really improving the conditioning of your measurement operator. So what we ended up having to do is calibrate different preconditioning for different number of spokes. And this is what can give us an algorithm that converges at a constant rate, no matter what the temporal resolution you choose for different time points. So this is what those curves look like. So technically, we did that just by restricting our Fourier operator to a k-space radius and computing singular values, computing maximum singular values of those restricted operator. So what you can see that is quite intuitive, if you take the 21 spokes, so the tightest temporal resolution, you see that you have this big tapering region here where you're undersampled and you just cannot do density compensation anymore, and you have this undersampled region, oversampled region in the center where you need to apply that filter. And as you increase the number of samples, this thing becomes flatter and flatter, and eventually it would converge towards the ramp filter. So just very quickly, so this is what the image would look like at the first iteration. So just to show you that we are still pretty far away from theoretical compressed sensing, this doesn't look like white noise. Because when you have these radial undersampled images, you can clearly see those streak artifacts. So that looks very structured. And then after reconstruction, this is kind of what we get. So another nice thing with that is that because we reconstruct at high temporal resolution, we actually can see information that was not available before. Because there has been work on pharmacokinetic modeling where basically chemists model how the contrast agent is going to propagate in the body depending on what you have within each voxel. So by modeling some proportions of intracellular space, extracellular space, and the porosity of the cellular membrane, they can basically regress some information about the tissue microstructure from these contrast curves. But so far, they had only 4 points on those curves, actually, to regress that. And they had 4 points that were biased. You see this big arterial pack here. If you have to do low temporal reconstruction, where you actually bind all those data together, you're not going to get that peak at the right value here. You're going to get it somewhere there. So that is something very, very exciting now, that potentially maybe this can even enable more clinical research, because now we finally have the data to be able to really validate those models. So that's what I wanted to present about compressed sensing, and I'm going to quickly go about some more recent stuff that we've been working on. So the first one is using deep learning for image-based image enhancement. So in that case, that's for low-dose CT. So that means that we get a clinical scan, we get a physical simulation of a low-dose scan where we just inject noise correctly in the raw data and redo the reconstruction. And we just learn a supervised system that's going to learn to do the inverse mapping. So why we want to look at that for CT? Mostly because it's very difficult to get something that radiologists like for CT. Because in CT, you have this principle of getting the dose as low as reasonably achievable. If your CT image is too good, then that means you're hurting the patient because you are subjecting him to too much dose, which means that radiologists are trained to look at images that look noisy. I mean, this is what we call our ground truth. I think no engineer would call that a noiseless image. So and so that means that if you show radiologists images that have been overly denoised, that are too smooth, they're just not going to like it. And so this is where deep learning can help, because our ground truth still has some noise, we can actually learn something that looks more natural than anything that we could do with a TV or wavelet transformer, and anything you could craft by hand. And the other thing is that because in the end we want to be able to deploy on the scanner, we want to learn things that are robust to any kind of variation that the technologists could do with the acquisition sequence. And so that means that the network takes as an input not only the image, but also any kind of metadata that we can learn to reason about. So things about the geometry of the reconstruction, how thick you reconstruct your slices, what is your in-plane resolution, what is the reconstruction kernel. So in CT, you always have some kind of low-pass filter that you apply when you reconstruct. And depending on that kernel, you're going to change the noise texture in your image. So things like that. So we take that also as the input of the network, and we have a special architecture so that we can learn how to, the network learns to adapt also when the scan changes. So we're also looking at deep learning for MR reconstruction. So there have been multiple approaches for deep learning for MR reconstruction. Typically, what people do would be to take an iterative algorithm and unfold it. And so train a network that looks like an iteration of your proximal gradient or your ADMM or whatever, simply because there is no convenient off-the-shelf deep learning architecture that can go from Fourier domain to image domain. So what we did is something like that too. But on top of that, we're trying to learn an FFT as well. So we also unfolded the FFT itself. So we took a Cooley-Tukey FFT, and we replaced basically all the filters that are in the Cooley-Tukey FFT with trainable parameters. Why we want to do that? First, because when you're undersampled, there's nothing that tells you that the adjoint FFT is actually an optimal reconstruction operator. So you can learn to do better than that. And second, because your Fourier sampling is actually dependent on what the scanner does, and you can always have some kind of physical inaccuracy, and so your Fourier matrix might not be completely accurate, and you might want to correct that. So this is very early work where we can validate that we get a small improvement when we train the FFT. If you look very closely at the images, you can see that there are some structures that appear, but I guess there's still a lot of improvement to do here. And also an interesting part is that if we're able to learn an FFT, then for generic network, that means that we could learn something that is fully convolutional, but that can also learn to go to Fourier domain to do something else if it needs to, and that might be able to train things that are more generic than just convolutional network. And finally, the last thing I wanted to talk about is about being able to adapt on the fly to different imaging settings, and also being able to be future-proof in a sense. tomorrow someone comes up with a new imaging modality or with a new MR sequence, I still want my algorithm to be able to run. So this is something that we're doing also for image-based denoising for MR, where the noise in MR is modulated in space because of the coil sensitivity. So you can see there's a noise band here. And you have a lot of contrast variability in MR depending on how you excite your tissue. And we want one single algorithm that work everywhere. So this is based on Shore. I don't know who here is familiar with Stein's unbiased risk estimation. Okay. Okay. So maybe it's worth going over it in detail. So that's a pretty beautiful result from Stein that says that, okay, let's say I have a noisy image X, and I know what the noise variance is, and I have a denoiser F. So this is something that is trying to estimate the ground truth noiseless image from my noisy image. So what Shore tells you is that you can actually blindly estimate the error that your denoiser is doing without knowing the ground truth. And so you do that by expanding this expansion, this expression, where you're going to estimate this by a term that is just how much your denoiser changed its input, and a stability term that is just the divergence of your denoising itself. And so basically, if your denoiser gives you something that is close to your input, and that is stable, that if you add some more noise to your input, it actually stays the same, that means it's a pretty good image. And so we can use that to on the fly tune some free parameters of the denoiser. And so I'm not going into the details of how we do it technically, but basically, if you add a few parameters in there, you can optimize this Shore. And so you can, if you know the noise covariance matrix, you can estimate the image prior statistics on the fly, basically. And so that's pretty much what I wanted to talk about. Thank you very much.